For our project, we worked with Conforta, a well-renowned security enterprise. Conforta provides software solutions to protect and manage data entrusted by Fortune 100 companies. In particular, we worked with Conforta's Secure Data Protection Suite, or Secure DPS, SDPS for short. SDPS is a tokenization-based data protection system and holds 6 major cybersecurity awards in banking, finance, and security software and the 17th Annual Cybersecurity Global Excellence Awards. This has been a great opportunity to get hands-on experience with data protection. With security being a major concern with technology, we are proud to be able to enhance the use cases of SDPS by making it available and the function as a service platform and supporting public safety. By doing so, we're able to use SDPS with the FAAS event-driven execution model to build, compute, run, and manage application packages without having to maintain their own infrastructure. We're able to leverage the platform without having to manage the servers and to allow for quick and easy functionality. Also giving us the choice to use different languages to write codes such as Java, Python, C, and others as well.
FAAS programs or functions are modular pieces of code which execute when triggered by an event. The FAAS functions run with the help of a container, a type of microservice that provides an environment in which the function can be executed. FAAS design primarily focuses on code as opposed to infrastructure, which the infrastructure can be maintained by cloud services such as Amazon Web Services, otherwise known as AWS. Due to their modular nature, FAAS functions are very scalable and can be scaled up or down based upon demand. Overall, FAAS is a more cost-efficient, it has less downtime, and is less complex to deploy than conventional solutions are. FAAS reaps the benefits of cloud infrastructure and analysis. Our objectives that we sought out to achieve were to conduct research in use cases, feasibility, and integratability of using Secure DPS in a serverless FAAS way, as well as building working proofs of concepts using the frameworks Azure Functions, Knative, Kubeless, OpenFAAS, and OpenWhisk, which OpenWhisk has since been dropped from the project. These functions shall signal the appropriate error codes, messages, and logs to the intended recipients. These functions shall also provide a secure methodology to load secrets such as SDPS authentication keys, credentials, and configurations, as well as authenticating usage of the functions using Kubernetes secrets. Clients shall be able to use and integrate SDPS on local premises. The project shall provide metrics and best effort estimates for installation and initial deployment alongside documentation for local development to the targeted architectures.
There were multiple problems encountered and overcame while developing our project. Since FAST technologies are relatively new, online resources detailing working with FAST technologies are more difficult to find. Furthermore, documentation for the frameworks were not extensive, and in some cases, team members had to comb through the source code of the frameworks to determine how to do specific things. There were also issues integrating Kubernetes and Docker with the Kubeless framework, as Kubeless is incompatible with the more recent versions of Kubernetes and Docker, and this fact was not documented very well. To solve the previously mentioned problems, we dug into GitHub issue threads to find compatibility issues, framework support, and various methods for fixing these problems. Furthermore, there were 2 rounds of testing to help fix any additional bugs that had gone unnoticed. This testing was done internally with several Conforta employees doing the testing who had either had experience with SDPS or Kubernetes, and resulted in several bits of constructive criticism. We learned from this feedback and improved our functions accordingly. The issues presented in the first round mainly involved error handling, edge cases, error reporting, and error codes. By the second round, we had solved the issues from the first round and received feedback affirming just that.
Our experience as a team has taught us a lot and has been very rewarding as an individual as well as a team member. Being a team of 4, we were each given the opportunity to lead the team equally by switching team leader roles throughout the project. This gave us an opportunity to communicate with our clients and enhance our professional skills. With this being a research project to generate the feasibility of different FaaS frameworks, we ran into issues with one of our frameworks called OpenWhisk. With this framework taking its time to set up and continuous degeneration of the pods, we as a team had to make a collaborative engineering decision to drop this framework. This required us to make changes accordingly in the requirements documentation and consultation with our clients. We were able to maintain agile development environment by constantly communicating with our clients in a weekly basis. We kept our team members updated on the tasks they were assigned as well as on their progress. We always schedule a meeting among our team members for any important decisions. We had a few miscommunications with our clients, which was resolved in a professional manner. We developed learning and researching skills throughout this project as we went from knowing nothing about FaaS to researching and implementing FaaS through our own efforts and resources. And lastly, to grasp a bigger picture of the project, it is estimated that we spent about 90% of the time in research and integration and the remaining 10% of our time in the actual function implementation. Here is the overarching timeline for our project. In August, we introduced ourselves to each other as well as to our client. In September, we created the first draft of our software requirements documentation. In October, we began our research on FaaS frameworks and created our first proofs of concepts using these frameworks. In November, we developed proofs of concepts that use the STPS Translator Manager, and in December, we had finished prototypes for all 5 frameworks using the STPS API. At the end of January, we regathered from the winter break. In February, we implemented functions with STPS version 6.0.0, and in March, we implemented functions with version 7.0.0, the latest version of STPS. In April, we prepared for user testing and focused on improving our handler functions based on the feedback provided by the testers. In May, we will be preparing to transfer the technology to Comforte.